Next topic is network models, and this is the OSI and the TCP/IP. And the first one, layered model benefits. When we talk about this, and you used to have one that says why models, why network models, and my thought a lot of times was to punish network students. But once you get into these things, they really do help you out, particularly in troubleshooting. The list here is less complex compared to not having a model, and less complex because when something's not working, what's not working? What layer of the model is it? Is it the IP? Is it the TCP? Is it the data link? What things aren't working for us, and what can we use to troubleshoot the things that aren't working for us? Standard interface is a really big deal. If you've been doing networking for several years, a lot of years, remember when we first started networking when I first started networking anyway, in the late 80s, early 90s, if you had a device, and we were using modems then, and you wanted to put a modem into your computer, you had to go to the manufacturer. You had to go to whoever the vendor was. If you wanted a NIC, you had a compact and you wanted to put a network interface card in it, a NIC in it, you went and got a compact NIC. If you had a Dell, you went and got a Dell NIC. But now, if you want to buy a device, video cards were the big one there, but if you want to buy a device to add to your computer, you go to one of the vendors and you just buy one because we have standard interfaces. Standard interface between each layer for multiple vendors to create products that fill a particular role. The benefits of open competition. And I think that you can see this I don't know if anybody is a Mac user. My son's a Mac user. If you go to buy a Mac or a Mac part, then you can't really add anything to a Mac because it's a closed system. And they're going to be more expensive. And the reason they're more expensive is because we don't have this standard. The IBM PCs don't support the dark side. The IBM PCs, if I actually were going to do a Mac, I think I'd just put Linux on because OpenBSD is the operating system that they're using for this. But anyhow, standard interfaces can be used. It doesn't matter who the manufacturer is. If you want a NIC, you can go to whoever and go to Best Buy and buy a NIC. If you want a video card, you can go buy a NIC. Easy to learn, more easily discuss and learn the details of protocol specifications. This is one that probably first look at the models is a little hard to swallow because easy to learn. So I mean easy to learn. I got to learn all of the things that go on at each of these layers, and yeah, we got to learn a lot of what goes on at each of these layers so that we can now use that knowledge to make life easier for us when we got to go fix something to do these things. Easier to develop or reduce the complexity, allows easier program changes and fast product development. The complexity and the standard interfaces and the multi-vendor, the modular engineering, we'll get to that. Yeah, that's the one that I want. But easier to develop, complexity, easier to program, faster development, multi-vendor interoperability. We don't. I think he's having a good time. Anyhow, that's happened to me before too. So anyhow, easy to develop, multi-vendor interoperability, all things that we can do. Modular engineering, and the modular engineering, one vendor can write the software that implements each of these things, and then somebody else can implement the lower layers. And Microsoft's TCP/IP software in the operating system is an example. One of the demonstrations of the availability or the desirability, I guess, of the modular concept is going on right now, because we're in a transition to go in the network layer to go from IPv4 to IPv6. You don't really have to change anything except the network layer, the support for the IP addressing scheme, and the routers have to be changed, obviously, but none of the other things. We don't have to go in and put in new media. We don't have to necessarily buy new NICs, and I say that because of the support for the IP. Well, we don't have to buy new NICs for the data link layer. We don't have to go rewrite the all of the programs that we use, the web browsers and those sorts of things. So we can change simply what's going on at the network layer, IPv4 to IPv6, to allow these things to happen. The models themselves, and you notice that this one over here, 1, 2, 3, 4, 5, there is a 4-layer and a 5-layer TCP/IP model. I was real happy with the 4-layer model, but then they decided to break the bottom 2 layers back out again into the physical layer and the data link layer. I was real happy with the network access layer. Network access layer down there, fewer things to remember, but it also one of those things is a NIC a layer 1 or a layer 2 device, and probably a layer both device, because it's got a MAC address on it, the data link layer, and we use it to access the network, the physical layer, to do these things. But we have the 2 different models that we use, the TCP/IP model, the OSI. OSI was the original, and it wasn't necessarily the way that networking worked. It just modeled what went on with networking. And when we look at these things, this is the way data flows. People ask, where is the computer? It's not in this. The computer's not in this stack. The computer communicates to the stack at the application layer with the applications to send data up and down from one to the other to do these things. So we have the application, and then the top 3 layers, the OSI, the session, presentation, application, get glommed together as the application layer. What we're concerned with in the Cisco world is data shipping. What the router guys worry about, configure, want to know about, are these bottom 4 layers here, the transport layer, network layer, data link layer. These are the ones that we're going to use in order to get the data from one location to the other location. So we're going to not really worry about the applications that somebody else's responsibility for there. There are a couple of different ways that they communicate. Adjacent layer communications, each layer supports the layer above it, is supportive of it, does support one to the other. So we do those. We also are going to have same layer or peer layer communication, that the session layer communicates with the session layer, transport from one device to the other. So we have the peer layer as well as adjacent layer communication that goes on with the modeling that we use for these things. The TCP/IP model actually models the way that data flows in the TCP/IP network. It was designed that way. OSI been around for a long time. Actually, when the OSI model was developed, there were some other vendors, NetWare, one of them, that already had their own models. So they never incorporated the OSI into those things. This takes all of the aspects from the OSI model and puts it into an actual data flow modeling for it. The layers that we have of the TCP/IP model, the physical layer, protocols for moving frames between adjacent nodes, for accessing the medium by the devices. So the physical layer is where we access the media. the media is not actually part of the physical layer. The voltages are, the timing is, the encapsulation, not encapsulation, but the encoding is going to be part of what goes on at this layer. The protocols encoding and transmitting data over the network media are going to be there. Hubs, and this says NICs, and I think you can say NICs at layer 1 and layer 2, and this is to me where the advantage was to have the data link and the physical layer combined here. Helped with that, but we have broken it back out. So we have these things: Ethernet, token ring, FDDI, and frame relay are things that are going to be defined at this layer. The data link layer encapsulates the data packets on the network. MAC addresses are going to be here. The devices that run at this layer are switches and bridges that operate here. We looked at the switch a little earlier on how it does that with the MAC addressing, that it builds the MAC address table and then looks at the frame that comes in and then looks at the destination MAC address and then switches it to the port that MAC address is associated with. Makes things much more efficient. It does switching in hardware, very high speed type, and we'll see how next Friday a switch, how much it gets in the 24 ports and how many bits per second is actually going on with these devices. It's pretty amazing when we look at those things. The network layer provides addressing and routing services. There are two types of addresses. We're going to have the administrative addresses, the temporary addresses, the changeable addresses. At the MAC layer, we have MAC addresses which are permanent or physical. And here we're going to have routing or addressing, and it's going to be IP addressing, which are going to be temporary. These change. These don't change. Yes, they can be spoofed. I get that. But they are permanent addresses. These are temporary addresses, administrative addresses that we can use on the devices. Controls congestion on the network. So we have some method if we get too much traffic, and what happens if we get too much traffic, we get a slowdown message. Don't send so much traffic. So it controls congestion. Transferring data from the source to the destination network when multiple networks are connected together, and routers and layer 3 switches operate at this layer. Layer 3 switches are, let's call them convertible switches. Convertible, that's probably spelled wrong. They start out life as layer 2 just like any other switch, but we can configure them so that they are able to do routing or actually switching using IP addresses instead of using MAC addresses. They're going to be a higher speed device than a router. Routers route in software, switches switch in hardware. Bridges bridge in software, switches switch in hardware. The transport layer, connection, establishment, communication services, and this is where we get our three-way handshake. The SYN, the SYNAC, the SYN, and then the SYNAC, and then the ACK. Protocols contains two important protocols: the connection establishment, and this is location. Let's say location to location. Connection establishment, because the session layer, if we have more than one conversation going on, the session layer is going to control it. But this is going to get us connected to a location to do these things. Defines protocols for end-to-end transfer of the data, along with error and flow controls. And we looked up here, and this one says it controls congestion. Flow controls here, we're going to have a slowdown, or call it choke packet, spelled wrong, but choke packet says, okay, you're sending me too much information. I can't handle it. Slow down with these things. The two protocols, TCP and UDP, connection-oriented, and then connectionless for UDP. TCP is also called a reliable protocol. We'll do it, but review here. Reliable protocol because it numbers all of the packets to be sure that they all got there. This one's just kind of a send and forget, a shoot and forget sort of arrangement. Actually, in UDP, the application usually becomes responsible to be sure that everything got there. So we have TCP, two protocols, TCP and UDP. UDP is designed for streaming for things that we don't want to acknowledge. TCP is designed for things that we really need to be sure that it got there, or we want to be sure that it got there in order to be able to use that the data is there. The application layer is the top three layers of the OSI model. Definition of the protocols, file, email, browser, encoding of the data contains the top three layers of the OSI model in order to do that. The socket services. Socket, probably a term you know, but a socket is an IP address and a port number. And it gives us a service that we're connected to. So if we have an IP connected to port 80, we're at a web server. 443, we're at a secure web server. And we can have multiple sockets defined at a single location. So TCP or UDP gets us to the site. And then the sockets here get us to the service that we want. The web server, file server, whatever we're doing, and web server is typically going to be there. We also usually get multiple sockets because we get all the ads that we don't want. All of the other things that open when we go to a web page, and all that's going to happen within the connection itself when we have those things. This is kind of a reasonable summary slide for the 5-layer model. The application, a group of applications requiring network communications, web browser to web server, for instance. The transport layer establishes a connection between applications on different hosts. So we have establishes the connection with a remote host. The IP creating the packets that move across the network. It transfers the packets with the virtual IP addresses. The data link layer, MAC address, responsible for creating frames that move across the network. Frames with the physical MAC addresses, and then the physical layer, the transceiver that drives the signals on the network. So it's going to be the bits, the ones and the zeros that go from one location to the other. Thing that you've seen before, we tried to see before, the applications here, the top 3 layers of the developer's realm. Shipping data, the bottom 4 layers of the OSI is the network engineers. That's where we're going to live. And how do you remember these things? And you guys have seen this. All people seem to need, yes, that's sleeping, but all people seem to need data processing. Yeah, you can do that. I always had trouble with that one. The one that I preferred was this: please do not throw sausage pizza away from the bottom up, in order to try to remember those things. So we have the modeling that we use in order to do this, and it really does come in handy for troubleshooting. The OSI model, when we look at it, the layers, we're going to have a lot of the same, a lot of overlap from these things. Physical layer, transmitting packets on the physical medium. Electrical and mechanical characteristics. The video this morning, what is the voltages, and what do the voltages represent? What's the timing? What kind of encoding are we using? That all happens at the physical layer. The truth is, if you look at these things in depth, the lower layers are much more complex than the upper layers. A lot more goes on down here. So it's going to receive the packets from the data link layer and put them on the medium. The NICs and the access points operate at this layer. NICs, access points, hubs are going to be at this layer. An access point is essentially a wireless hub, but everything's connected to everything else. And since it's wireless and it's flowing around, running around in the atmosphere, everybody can see everything that goes on with it. The mode and the medium determines the mode and medium of data transmission. The PDUs and the PDUs here, protocol data units, and this one is going to be bits. And when we get done with these, let me give you an acronym to try to remember that, or a little saying to try to remember those things. The data link layer, transferring frames between adjacent nodes without errors. And the key here is adjacent nodes. We're not going to another network. The adjacent nodes, the ones that are connected to each other. And if we're connected through a switch, these are going to be adjacent nodes. We have a computer here with a Mac and a computer here with a Mac. These are adjacent nodes. They're going to communicate directly through the switch, and the switch is going to switch the data to the port that MAC address is associated with when we do those things. The PDU name here, and then we're going to have frames at this layer. It does have sub-layers, the logical link control and the media access control, the MAC. The media access control is the CSMA-CD. The logical link control is I like to call it a protocol router. What it basically says is IPv4 or IPv6. What's the next protocol? So let's just say next protocol. That's going to be used in this thing. So we have the sublayers, the PDUs, the switches are going to operate at this layer. The network layer is responsible for addressing, and this is going to be for IP addressing. This up here is going to be MAC addressing. Again, we have two different types of addresses. The MAC addresses, the permanent addresses, the burned-in address, Cisco term BIA burned-in address. And when you look at the properties of an interface, it will say BIA, burned-in address. Selecting the best route and routing packets from the source to the destination through the network, destination through the network. It's going to find networks. Because the IP addresses, the IPs change. The MACs don't change. So what we find the individual device with is the MAC address, the fixed address, the burned-in address to do these things. It controls congestion by making routing decisions. What's the best path to get there? We're going to have metrics, and each of the routing protocols is going to have a different metric. We're going to have metrics that help us to find the best path, or allows the router to find the best path. Routers and some switches operate at this layer. The some switches are layer 3 switches. Layer 3 switches will be operating at the network layer. Interconnecting two or more similar networks, and the PDU name here is going to be packets when we do that. And again, give you a little hopefully a little saying that will help you remember those. The transport layer, and this is the big one here. The transport layer, it's got a lot going on. Establishes, maintains, and terminates or reestablishes connections between devices. Controls how, when, and how long a device can transmit and receive data. Specifies the procedures for connection, termination, and reestablishment. Accepts data from the upper layers and breaks it into smaller units known as segments, and that's going to be the PDU here. It's going to be segments. Passes the segments to the lower layers, that all segments arrive correctly at the receiving end. So this is going to be the numbering system that we use, that we established with the three-way handshake. One of the things that it's going to do is to establish the numbering system, adds the sequence number to each segment, to reconstruct the original sequence. The data may arrive out of order. I think all you guys were probably in the military after, those of you that were there, after we used letters. At one time, in the Navy on ships deployed, when you write letters home, you never know when they're going to go out, or when they're going to get there, when they're going to be delayed, or when they're going to drop them in the water when they're doing the transfer, the helo transfer for these things. So you would number the letters 1, 2, 3, 4, 5, 6, and they might get home as 1, 3, 6, 4, 2. So you know, and then I guess we'll put 5 in here after that, so that the receiver knows that, you know, if I'm reading this one and it's number 3, I may be missing some stuff from 2. What this does, the TCP does, is when it gets to the destination, it puts the data packets back in order so that they make sense from one to the other. Error correction sends acknowledgments to the network layer. The error correction is when it doesn't send an acknowledgement, we get the information retransmitted. The PDU here is going to be the segment for TCP or the datagram for UDP. The session layer keeps the different conversations separate by assigning port numbers to each process using the network. And remember, we have the IP address from the transport layer, and then we're going to have the port number here, and the port number, and this is one that the port number kind of gets, I don't know, messy, a little messy, I guess, but we have sockets at the session, and the socket's going to be an IP and a port number. And each of these things is going to have a socket. Our device, our machine, is going to produce a socket. It's got an IP address, we know that, and it's going to assign itself a random port number so that the question and the answer can go specifically from one location to the other. And then we go to a destination, an IP, and a port number. If we're going to a web server, this would be an IP address. It would be port 80. It would be the socket when we got there. And it would come back to our ephemeral, our temporary port, and the port that's assigned to it using sockets. And I guess one of the ways to think about it is like an electrical socket. You plug something in, then you have a resource. When you plug something in to the IP address and the port number to a web server, for instance, you've got something. You've got a connection to the web server. We have to have sockets on our devices for it to come back to. The devices at the destination are going to be the well-known ports. The well-known ports, the port 80s, the 23s, the 20s and the 21s, and those 69s, 123, some that you've heard of and some that you haven't heard of that I'm talking about. But we have to have that sort of connectivity in order to have the data flow that we want to have with these things. Presentation layer, encoding the data into a standard compatible format. The presentation layer is actually responsible for being sure that the application layer can read it, that it has that particular capability for those things. Standard data formats are going to be used here. The translation at the presentation layer is an intermediary format and will change at the lower layers. They don't have to be there. Add services, data compression and encryption. And encryption is probably a big deal here. We do have encryption. The encryption is going to happen at the presentation layer. And the PDU name here is data, but the PDU name at the top is going to be data for these things. Application layer provides utilities and services that allow applications to access the network and its resources. this is going to be utilities and services. These are services. What runs at the application layer? A web server, an email server, a file server, an FTP server. Those are going to be services that are going to be at this layer, at this level when we do these things. Defines protocols for tasks such as transferring files, sending emails, saving data to the network when we do those things, and advertises itself to the server resources to be available. The only layer which the user interacts. I want to put in a blank slide here so that we can do these PDUs, and let's see if I can scroll them out. PDU, that we have the application layer, and then we would have what? Transport, and then network, is that right? Data link, and then the physical. The PDU in the application layer is going to be data. The transport layer is going to be segments. And bear with me. The network layer is going to be, going to be packets. The data link layer is going to be frames. And the physical layer is going to be bits. How do you remember this? How about don't some people fight back? Back. Spelled back wrong. I almost made it. Don't some people fight back? That's lots of different little sayings on how to remember things, but the PDUs, the protocol data units that are named, those are the names. The data, segments, packets, frames, bits, don't some people fight back? Hopefully a way to help remember those. Let me get rid of this one. And then the similarities that we have for these things. And, I guess we show this multiple times here, but the application layer, the top 3 layers of it, the transport network, data link, the bottom 4 layers, the ones that we're concerned about with data shipping, are going to be the same. They have similar architecture. Both have application transport network layers, and both have their lowest layer connected to the physical network when we look at these things. And the PDU, segments, packets, frames, bits, the encapsulation terminology or the protocol data units that go on with these things. The memory tool, don't for data at the top, which doesn't show here. Some people fight back to try to help remember those things. So the OSI in the TCP, the OSI standardized the 7-layer model, the original model that we had. The TCP/IP model developed to execute the internet-related tasks. It was developed by DARPA, the Defense Advanced Research Project, who actually did invent the internet, or at least had a major hand in doing that. 5 layers, and you will see 5 layers and 4 layers. You'll see both. 5 layers kind of new to me. 4 layers has been around for a long time. Originally was called the DoD model because, again, they're the ones that invented it. The application layer handles the responsibility of the application presentation session layers. We combine those instead of trying to break them out separately. All of those things happen at that location. Another kind of summary slide, and I think this is a fairly reasonable summary slide. What goes on, or summary image, what goes on with these things, what goes on in this model down here. We have the physical layer down here and the protocols that we have at it, and what is involved here, the media, the signal, the binary transmission for those things. And we go to the data link, Ethernet. What protocols do we use? And we have some LAN protocols and we have some WAN protocols. The difference in what really defines a LAN and a WAN are the protocols. The physical addressing is going to be at this layer when we do these things. PPP, token ring, and then kind of images for what we're going to have at each of these layers. We have the MAC layer, router MAC to go on to these things. And then we go up to the network layer, path determination, logical addressing, the protocols that we use here, IP ARP, IPsec, ICMP, IGMP, OSPF, routing protocol are going to be here. And then the devices, images of the devices that we're going to be using at this layer. And this is the router and the wireless router that we would have. And then at the transport layer, the protocols, TCP, UDP, SSL, TLS, SCTP that goes on here, end-to-end connections and reliability for this thing. The numbering system, the three-way handshake in order to get it started. The session layer, the session establishment in TCP, SIP, and SIP is an IP phone protocol that we use. RTP, real-time protocol, name pipes, and the devices that are going to be here. And when we get to this layer, this is showing bridges that go, and these are different bridges, not the layer 2 bridges that we were talking about. And then the presentation, recognizing the data representation, and encryption that goes on with it, and then the network processes and some of the services that are running at the application layer. The web servers, the point-to-point, to here the emails, SMTP, the email and the POP, which is the receive, and the SMTP is the transmit. Telnet, FTP. Devices that are running or applications that are running on the services that are running on the devices.